In the last video, we took a look at what Stokes' theorem was saying and what exactly we could use it for. It bridged a connection between a work integral, that's specifically a line integral that we have over here, and this surface integral with the curl of f. Now again, since both of these things are equal, we can use Stokes' theorem to help us shortcut either the calculation of a line integral like the one on the left, or of a surface integral like the one on the right. And in the next two examples, we'll actually see how this is done. Let's take a look at example 5 to see which direction of Stokes' theorem we're interested in moving in. So let's see what we have here. Suppose that C is a curve, and it's the triangle which is traced out by moving from this point to this next point to the final point. And then to this final point. We want to use Stokes' theorem to help find the exact value of the work done by the force field, F, in moving a particle around the curve C. Okay, so let's try to get a little bit of context here in terms of what's happening. So we know that we're going to have, I'm going to go ahead and shape up a nice little 3D axis here. So I know that we're going to be working with a curve that starts at, let's see, 0, 0, 1. So let's imagine that I'm starting up here, 0, 0, 1. I'm going to go to 1, 0, 0. I'm going to go to 0, 1, 0, and then back to where I started. Okay, so if I was to draw this out, I'm connecting from here to here. Then I'm connecting from here to here, and then finally from here to here. Okay, and so I kind of have enclosed up here, you can see a surface, right? There's a surface that's getting enclosed by this. Okay, now what I'm interested in calculating here on this question is apparently the work that it takes to go around this curve, or the work done by the force field in pushing a particle around this. Okay, so let's see what we would have. Stokes' theorem would allow us to say that if we want to compute that, we could, instead of computing the direct work integral, which again would require parameterizing each one of these individual sides, and then calculating a line integral along the slant, and then the horizontal, and then the slant again. Well, doing that would be 3 separate line integrals that would be a little bit difficult to work with. But instead, Stokes' theorem says you can go ahead and just set up this double integral, this surface integral that we have over here. Okay, well, let's see how this would work. So we have all the pieces that we need, and so we'll go ahead and start to take a look at our surface that we have over here. That's our surface sigma. We want to understand that surface and the things that we can say about it. Okay, so let's see. I'll say we see from the picture that sigma is, well, it's really just a portion of a plane. And I bet I could even figure out exactly what that plane is given by, right? That is, like, what's the formula for that particular plane. Notice here that, again, if I'm crossing at 1, 1, and 1 on each of these, it's probably no surprise that I could come up with the equation of a plane that looks like this. Because notice that whenever any two of the coordinates are going to be 0, the other one happens to be 1. Of course, if I was to go ahead and simplify this a little bit, I could turn this into a z equals formula, right? By just sliding my x and my y over to the other side. Now, I could go ahead and think about the fact of what I need in order to be able to use Stokes' theorem. I need to be able to go ahead and see here that this is a curve that appears to have an orientation, but I want to make sure it has a positive orientation. So if I was to walk around this curve, I need to think about if I would rather have my head facing up or my head facing down, so that way I could, when walking along the curve, reach out with my left hand to touch that surface. Well, it might be easy to see that if I imagine this surface as being oriented upward, that is, I have a person that stands on my surface like this, then when they walk around, they're going to be able to reach out with their left hand to touch the blue space. So we can go ahead and assume that this sigma has a positive orientation. So we'll say this has positive orientation, right? It's pointing upward. Now, we want to go ahead and try to think about a couple other things. We want to determine the values of x and y that would ultimately yield this particular surface, right? We want to know, like, what's the region that we're working over. So I can go ahead and state this. So I'll say if we project sigma to the xy plane, we get, and I'm going to go ahead and try to draw this out as well. Well, let's see, if I draw a little xy plane here, and I think about the picture that I'm going to end up with, I know that I'm going to have, let's see, starting from x is 1 to y is 1, I'm going to have a slant that goes there. And notice I'm going from x is 1 up to y is 1. So that's my line that kind of goes like this. And this, of course, is a really, really easy curve to go ahead and describe. This would be y is equal to 1 minus x. So if I was to have that, I can see that what I have down here is a separate little region that we can call D. This is the region that this plane exists above. And so I can go ahead and think about ways that I could begin to describe this region. So I'll state here, we see that my region D is a bunch of x comma y points such that, and let's say here that y is going to be bounded from 0 to 1 minus x, and that x is bounded from 0 to 1. Right? That seems like an easy way to try to set this up. Now, I can see then that my surface is ultimately given by this function then up here existing over this particular space. So I can now go ahead and start to think about how Stokes' theorem can be applied. In Stokes' theorem, I needed to have a surface with positive orientation, I needed to know what it existed over, and I also needed to have the curl of f defined. So I'll also say up here that, oops, let me back that up. I'll say that we calculate, let's see, our curl of f is going to equal, let's see, partial with respect to x, and this is going to be of x plus y squared. Let me put these in first just for spacing purposes. Partial with respect to y, partial with respect to z, I, j, and k. Okay, so if I was to set this up, let's see what we come up with. My curl is going to be partial with respect to y, so that's a 0. Partial with respect to z, 2z. Then I'm going to have a minus, and partial with respect to x, I'm going to have minus 2x, and minus here a 2y. So I'm going to get this. And my final component is going to look like partial with respect to x, which is 0, and minus partial with respect to y, which is 2y. So if I was to simplify this down a little bit, I end up with, it looks like, negative 2z, and then I'm going to end up with my last component being negative 2y, and, oh, I might have accidentally miswrote something here. Yeah, I accidentally miswrote what I had in here. This should be partial with respect to z of x plus y squared. So, whoops, this right here should not be a 2y, but instead that part should be a 0. So this should be a negative 2x in there. My apologies. So here's my curl. Okay, so now I can go ahead and I can think about setting up this double integral. I'll say that by Stokes' theorem, if I want to do this work integral along C, that's instead equivalent to this double integral over sigma with my curl of f ds. Okay, so now I have to think about how I'm going to go ahead and try to compute this particular surface integral. Now, one thing that I might notice again is that since my surface is given by a function, and I don't have to parameterize it, I can take the easy steps that we had talked about for when we have a function and we want to compute its surface integral. So I can go ahead here and recall that this is actually just going to be equivalent to doing my double integral over D, where that surface is defined. I can input what my curl of f is actually going to be, which in this case is my negative 2z, negative 2x, negative 2y. And I can also multiply that by, you might recall, that I could do my gradient of g, and then multiply that dA. Now remember that capital G is going to be equal to my z formula minus my 1 minus x minus y. So this is, it's equal to z minus 1 plus x plus y. And thus, my gradient of g is going to be equal to 1, comma 1, comma 1. This is the approach that we took whenever we were computing a surface integral for a function. And so we're just, again, utilizing that here. So notice if I was to take this gradient g and I dot it with my curl, this is actually going to be super, super simple. I'm going to just end up with a double integral over d of negative 2z, oops, not plus, but minus 2x and minus 2y dA. I have exactly what I need here. Now, of course, I can go ahead and recognize that my dA is going to be some combination of dx and dy. I have my bounds on my region D, but I'm going to need to go ahead and replace what I end up with here in z. I need to go ahead and recall that z itself was actually equal to 1 minus x minus y. And so if I take that, minus 2x minus 2y, dA, I'm ready to go. Now I can easily go ahead and imagine setting up a dx and dy and like using the bounds that I had on that region to set up this double integral. But fortunately here, this is actually going to come out to be even a little bit simpler. Because what I'll notice is that if I do some distributing here, I'm going to get a negative 2 plus a 2x plus a 2y and then minus a 2x and a minus a 2y. Now of course what that implies is that my 2x's are going to cancel out, so are my 2y's, and I'm really just going to be left with an integral that's going to look like negative 2 times the double integral of 1 dA. And again, that represents the area of the region D. However, the area of the region D is so easy to find because it's the area of a triangle. So let's see, I would do 1/2 the base, which is 1, times the height, which is 1. So this is negative 2 and then area of a triangle. 1/2 the base times the height. And so ultimately what I end up with here at the end is a value of negative 1. So we actually went ahead and were able to use Stokes' theorem to help us try to determine this work integral, this line integral that goes around the outside. We could have calculated this directly by just doing parameterizations of each one of these line segments and then going ahead and doing 3 separate line integrals, but Stokes' theorem gave us a different way. Of course, what you're seeing here is that it's a little bit complicated of a process, or at least it can appear to be a complicated process. It requires that I understand everything that we talked about with surface integrals back in 5.5, because it's usually right here that people struggle. How do I actually replace this ds at the back? And remember that if I had a parameterization for my surface, I would do something like my partial with respect to u cross partial with respect to v. And then I'd put a dA at the back, something with the du dv. But if I have a function, then I can put the gradient of g as we defined it here and dot that in. So there's a lot that's going on here that we have to make sure that we understand. Of course, this requires a decent amount of practice. In the next video, though, what we'll do is we'll take a look at how I can use Stokes' theorem in the reverse order. What if I wanted to compute something like a surface integral, and instead I choose to opt to compute this work integral, which has the same answer?